Okay, let's move on. Now we have a SVM loss function, something like this, right? So this loss function is based on the hinge loss, right? So comparing to the previous logistic regression function, the SVM method or SVM loss function can guarantee the much larger margin case in terms of the training set. Okay, so this is called the SVM. So to recap, the shape of the hinge loss function looks like this, right? So yeah, let's say that this is the hinge loss. So first of all, to find this mapping function, or to find this w, the parameter that minimize this cost function on the training data set, we have to find the w, right? Then to optimize this loss function, we need to analyze the shape of this loss function in terms of w. So there is two concepts: the convexity and differentiability. So what is the convexity and what is the differentiability? Actually, these two concepts are out of scope of this lecture, but this is very important concept in the optimization technique. So if you have some chance, please try to understand what is the convexity and what is the differentiability. So I would say the convexity in 2D domain is looks like this. So in this case, there is only single global minimum in case of convexity, right? So this is the very desirable property that we want to get in designing the machine learning, our machine. And there is another concept of the differentiability, something like this. So okay, let's say this is the function w with in terms of w. In some case, we need to find the derivative of this loss function L over w in terms of the with respect to w. Okay, so but in this case, there exists the derivative of the L of w for whole w, right? But let's see the this hinge loss case. First of all, when you think about the slope or the derivative on here, there exists the derivative, right? But here, there also exists the slope, right? But what about this point? This is not differentiable, so in this case, we cannot get the derivative of this term at this point. Okay. So in this case, we can't use the some kinds of the techniques such as the normalization. So to solve this optimization, we have to use some kinds of the iterative solver, such as the gradient descent with the subgradient, because in the gradient descent we need to compute this term, right? But in this case, we have to use the subgradient. That is the hard to optimize. So the question is there any better optimization algorithm here? The answer is yes. So from now on, we will derive the new loss function that replaced this original SVM loss function. Okay. Before that, we need to introduce the duality concept. So what is the duality? What is the duality? Actually, duality concept is the very important theorem in the mathematical field, and there are so many theorem and so many concepts behind in the duality concept, duality technique. So it is hard to introduce and it is hard to present every concept of the duality in this class. So today I will just to briefly introduce what is a duality and how can this concept can be how this concept can be used in the SVM loss function. Okay, so first of all, let's say that we are interested in optimizing the loss function L of W, and let's say it is a difficult problem. For example, like SVM. Okay, so the concept of the duality is that instead of optimizing the loss function LW directly, we want to introduce the new auxiliary function called the G of W alpha, such that original loss function L of W is equal to maximum G of W alpha in terms of alpha, right? So, in other words, if there is some kind of the auxiliary function G of W alpha, we can rewrite the original optimization function, let's say the minimum of the L of W in terms of W. This is our original optimization. Then we can rewrite this optimization technique something like this, right? From this definition, right? Then we can say that this problem is a primer problem. Then why is it important? In this case, we can switch the minimization problem and maximization problem. Then we can get the new optimization function with the maximization in terms of alpha, minimization in terms of W with this auxiliary function. So in this case, this term called the dual problem. So in this case, rather than directly minimize this loss function and find the W star using the dual problem, we can first minimize this dual problem in terms of W, right? And then we can derive the parameter W in terms of the alpha star, something like this. So by using this dual problem, we can solve the much easier problem here than this problem. So that's why we are introducing the dual problem or the duality technique. Okay, so it means that if there is some kind of the dual problem of the SVM loss function, we can find a much easier loss function for the SVM. So here are some questions. So to derive the SVM function in duality concept, we have to find the three kinds of answer for each question. The first one is, how do we set this auxiliary function? Okay, let's say there is some original function here. Then we want to find this auxiliary function, right? Then we have to check when is it okay to switch the minimization in terms of W, maximization in terms of the alpha. Okay, so to solve this one, right? Then final one is the when the dual problem is easier to optimize than the primer problem, right? The reason that we need to use the duality problem is the dual problem. Dual problem is the much easier to solve the primer problem, right? So we have to check the dual problem is the much easier to solve, or the more much easier to optimize than the primer problem. Okay. From now on, let's answer the following question. First of all, the first question was the how do we set the GW alpha? How do you set the GW alpha? Before that, let's define a new function first. Okay, let's say that blanket Vn plus is equal to maximum of the 0, Vn, right? Then here, actually this one was the 0 if Vn less than 0, right? Or it will be Vn itself if Vn is larger than 1, right? So in this case, we can derive the new equation, something like this. Maximization alpha n times Vn in terms of alpha n, where alpha n is larger than 0 and less than 1. Why? Here's the proof. Actually, there's two kinds of case, right? The first case is Vn is equal larger than 0, then maximum is just what? Vn, right? Attain when alpha is 1, right? Another case is Vn is less than 0, then maximum is 0. Attain when alpha is 0. So by using this proof, we can say that this notation can be represented something like this, with the alpha n like that, right? So by using this one, we can rewrite the hinge loss here, something like this. Why? Because yn are here, and vn are here. So in other words, we can rewrite this term using this new notation, something like this, right? So in this case, instead of just finding this network parameter w, now we have a new parameter alpha n in this optimization problem. Okay, so from now on, we can solve this w of alpha, g of w alpha, and we can exchange or switch this minimization and maximization problem using the duality technique. It means that in the original optimization problem, we have to find the minimization L of W in terms of W, then we can switch this problem as a maximization alpha and with the minimization W in terms of G W alpha, right? So now we have a new loss function for the SVM technique, okay? But yeah, and comparing to the previous loss function, it is differentiable. It is the differentiable, something like this, and convex in terms of W and concave in terms of alpha. What does it mean? Let's see the figure in the next slide. Okay, so the second question is when is it okay to switch the maximization and minimization problem? Using the min-max theorem, actually you don't need to worry the what is the min-maximum problem, but just remember the using some kind of the theorem, it is okay to switch between the maximization and minimization when GW alpha is the convex in W and concave in alpha. Something like this. What does it mean? Here's the figure. Okay, there is a 3-axis. Let's say first axis means the alpha, second axis means the W, the last axis means the GW alpha. Okay. Then if the loss function is concave in terms of alpha, the shape of the loss function looks like this. It means that there is only one single global optimum, right? Then, okay, let's say this is the concave in alpha. What about the convex in W? What about convex in W? The shape looks like this. Okay. In this case, this is the convex in W. Okay. In this case, there is only single point here that simultaneously satisfy this term and this term. This one, and this one, and this one. So this is called the saddle point. What does it mean? If the loss function, if the mapping, if the auxiliary function G of the W alpha is concave in W and convex in alpha, then we can say that rather than solving this original function, we can solve this switched version of the loss function, which will be much easier to solve than the original one. Okay, so this is the min-max theorem. Okay, so it means that this original this is a new loss function that is related to the maximization in terms of alpha, minimization in terms of W. Okay, let's use the different color. Maximization in alpha, minimization in W. Okay. Now we want to solve this one first. I mean, if we can find the W in terms of some function of the alpha, right? Then we can represent the alpha. We can find the alpha from this problem, and then finally we can get the W from the estimated alpha value, then which will be our final goal, right? So this is our strategy. So how can we find the W of alpha first? How can we find this one? Because this is a quadratic function, we can just find the derivative with respect to W, something like okay, this is the GXW, right? and alpha was fixed. Then in this case, we can solve the correct derivative g of w alpha. Then find the w when this derivative is equal to 0, right? Then what is alpha that satisfies this equation? It will be looks like this. Okay. Actually, it is hard to. It's not hard, but it takes some time to derive this relationship from the original this equation. So I suggest you to this one yourself using some kind of the derivative rule in the matrix or the vector domain. Okay. Anyway, finally we can get the w of alpha is equal to 1 over lambda x matrix x transpose times y matrix y times vector alpha. Okay. In this case, y is the diagonal of the label y, something like the y1, y2, y2, yn, 0, 0, something like this, and x is the some kind of the vector that consisting of the input vector, right? Like this. So using this term, we can replace this w here and here, right? Then finally, we can get the new function here, something like this. Interestingly, there is no w anymore, and this loss function is only defined with respect to the alpha, right here, right? So it means that we can just solve this one in terms of alpha. Then if we find the alpha, then we can solve the w of alpha from here. Then finally we can get the machine parameter w that we want to solve. Okay, so this is the strategy of the SVM technique using the duality. Okay, so interestingly, please see this part. This is the just matrix, right? Right. So from here, rather than solving the original problem, we can just compute the matrix form of the input and output data, something like this, and can just solve this one in the very efficient way. Okay, this is our final optimization function in SVM. By the way, in here, this is called the kernel, which will be discussed later in this lecture. Okay. Anyway, so this is our final loss function. Okay. And final question was when is the dual problem is easier to optimize than the primal problem. Okay. From here, dual problem is differentiable, but constrain the quadratic problem, and dual problem is the naturally kernelized with the case x times x transpose. So it has very it has many advantages, which will be discussed in the later. And the final advantage is the solution alpha is typically sparse. So it means that it is the only non-zero for the training example that are instrumental in determining the decision boundary. What does it mean? Let's see the figure. So when we minimize this function, there is three kinds of the non-support. There are three kinds of the input x or the vector. So first kind of vector is a non-support case, non-support vector case. What does it mean? The non-support vector or the non-support samples lies on the correct side outside the margin. Here's the margin. What does it mean? Looks like this. Okay, so this is a Lysian boundary, and this is the negative sample, and this is the positive sample, and this term, this example, and this training sample collect side on outside the margin, right? So this is because this is a margin, right? So this is a non-support vector case. So what does it mean? In this case, this non-support vector makes some values here. Let's say this is the W transpose X, something like this. So in other words, these values doesn't contribute on the loss function because this is only 0. So yeah, this is a non-support vector case. Another case is a essential support vector case that lies just on the margin, something like this one. So in this case, it's just here. So it will be the some values from 0 to 1. So yeah, this is the essential vector case. The last vector is the, where's that? Yeah, bound support vector case, something like this one, that lies strictly inside the margin or wrong side, like this one. Okay, so in this case, they are here, something like this. So these samples contribute to learn this decision boundary rather than this one and this one. Okay, so this is the bound support vector. So by just analyze this alpha value, we can see the what is a non-support vector and what is the essential support vector and what is a bound support vector. Okay, so actually, as I mentioned previously, the support vector machine or SVM is one of the most popular one in the machine learning field. Even though the most current methods are based on the SVM, based on the deep learning or the neural network, SVM is still very powerful technique to solve some kinds of the classification problem. Okay, but and there is some issues with SVM. The first one is that there is no obvious probabilistic interpretation of SVM, right? Actually, in the logistic regression problem, we introduce some interpretation in probability when classifying some training set, right? But in SVM, there is no probabilistic interpretation. So that is the one limitation. Another one is that extension to multi-class SVM is the non-trivial. So it is easy to just follow the multi-class SVM. So please search what is multi-class SVM in the website. Okay, so this is the issues SVM. Okay, so here's one more concept in today's lecture. This is the kernel trick or the kernel technique. What is that? Okay, let's go back to the SVM. The solution W the parameter W has a counterpart alpha, as you can see here, right? So using the duality concept, we will establish a relationship between the W and alpha, right? From the previous slide, right? Then which will lead the way to kernel. What does it mean? Okay, let's see the example. First of all, let's think about the linear regression problem with the regularization, right? So if you remember the regression problem here, the loss function is going to be looks like this, right? If you don't understand what is this, please go back to our lecture 3 because there is the related mention, related text in the text for the regression problem. Anyway, in here, this is what output, right? And W is the what parameter, right? That we want to solve, right? Then this is the input or the input feature, right? How can you solve this? There were two kind of solution. The first one is what? Gradient descent algorithm. The second one is what? Numerication, right? So in this case, let's think about the numerication because this is a quadratic function. So for each solution, we have the numerication solution, something like this. If you don't know what it is, please go back to our lecture 3 for the regression problem, okay? Anyway, from here, we can just derive the new term, something like this. And if we define or if we introduce a new term alpha here, then this W star is going to be X transpose times alpha star, something like this, when alpha is something like this, okay? So this is the definition of the solution, the numerication solution of the regression problem, right? So let's see here. Here, in the solution of the alpha star, there is some kind of the matrix multiplication here, right? So in other words, this alpha star is expressed in terms of the matrix X transpose times X. So this is called the kernel matrix. Okay. So why we need the kernel matrix? Because there are several advantages of the kernelized regression. First of all, it is the computationally efficient in some case when solving the system of equation. As I mentioned previously, to solve this equation, there are two kinds of methods. First one is the gradient descent. Second one is the numerication. But comparing to the gradient descent, if we introduce the kernel matrix, the numerication is much computationally efficient than the gradient descent. Why? Because the kernelized technique. Because if we have the input feature vector, we can just compute the kernel very efficiently. So if we can do that, this is much computationally efficient than the previous optimization technique. Okay, then another case is by defining the case equal to X transpose S, we can work directly with the K and never have to worry about X. What does it mean? This is called the kernel trick. So what does it mean? Which will be discussed later, but to estimate this alpha value, actually if we have the kernel, we don't need to know the x, right? Because this is just a term that have the matrix x, right? So by using the kernel technique, we don't need to consider the x anymore. Just compute the kernel matrix. So this is very I'd say this is very beneficial. Then compute the x itself, or consider x itself. Okay. The last advantage is the working with alpha is sometimes advantageous. Provide the additional information for each data point or each training sample. For example, as in the SVM, let's go back to here. By analyzing the alpha n here, we can determine which training point contribute to train our machine. Okay, so with the kernel trick, we can introduce this alpha value, right? So this is the advantage of the kernelized regression problem. So here are some examples of the linear kernel or the kernel. Okay. Let's say there is the training data feature like the x1, x2 through the xn, right? And let's say the vector x1 is equal to x11 x12 through the x. Okay, sorry. Let's rewrite again. x11 x21 through the xn1, something like this, right? Then let's say there is the n samples or n training samples. Okay. Then in this case, we can make the vector x by using those samples, something like x1, x2 through the xn, like this. So what is the size of this matrix x? What is the size of this matrix x? M by n, right? Because the length of this one feature vector is the m, okay? So in this case, let's compute the kernel k is equal to x transpose times x. So what does it mean? X transpose is going to be xt transpose xn transpose with the x1, x2, xn, right? Then what is that? This compute this vector times this vector, right? What about the next one? This vector times this vector, right? You know how can you do that, right? So by using this matrix multiplication technique, we can find this value, something like this. So this is called the linear kernel. Then we can also introduce a basis function phi of x. Why we need this? Let's see this here. Okay, we have a vector x, input vector x, and we introduce some kinds of the kernel function here, right? Let's say something like this. But actually, if we just compute this inner product in the kernel matrix, actually it might be some limitation to model the nonlinear mapping relationship in the training data set. Because in some case we need some more higher dimensional feature, something like x square or the root x or the x how can I say x 1 over 2, something like this. So let's say there might be some kinds of the nonlinear mapping function or the basis function that containing this one, right? Then we can derive the new mapping function, new kernel, something like this. So we can say that rather than considering this one, by considering this one, we can compute and we can deal with the more nonlinear relationship in the training data set, right? But it is really hard to find this mapping function and really hard to define this nonlinear term. So the beauty of the kernel technique is that we don't need to consider this one. If we can find the new kernel function from here to here without considering this one, that approximate this nonlinear function, then we can get the similar property just considering this kernel function, right? So in other words, if we can develop a good kernel function without considering this basis function, that we can get the we can produce the similar output without considering this one. Okay, so this is the advantage of the kernel function. Okay, so in other words, the advantage of using kernels is that we don't need to specify this nonlinear mapping function. We can just work directly with this kernel matrix here. Okay, so if we have a very good kernel function that approximate the nonlinear relationship between among the training dataset X, it will be more efficient and more effective to solve our machine learning problem. Okay, so kernel function X and X comma X, and compute the I comma j, the entry of the K matrix K is going to be Kij, something like this, and in this case the kernel is represented like this. For example, if we define the linear kernel Kx comma X X, something like this, in this case the mapping function is just X itself. But if we kernel function looks like this, the mapping function looks like this, right? As we mentioned here, we don't need to derive this one. We just need to define the kernel function something like this. So this is the advantage of the kernel trick, something like that. And this is those samples are just the polynomial kernel. Another case of the kernel is the radial basis function kernel, which are defined something like this, right? So actually this is a Gaussian kernel or the Gaussian function. So if you remember the Gaussian shape, something like this, in 1D case looks like this, and 3D case something like this. So this is the Gaussian kernel things, right? So rather than using just a linear kernel, by using the uh, RBF kernel or the Gaussian kernel, we can consider the nonlinear shape, right? So what does it mean? If we go back to the SVM case, right? Here, this is just a linear kernel, right? This is just a linear kernel. Then let's say this is the K, linear kernel K. If we just replace this linear kernel K as a more higher dimensional kernel, something like the Gaussian kernel, then this SVM case can deal with the nonlinear relationship, something like this, rather than just straight line like this. So this is the concept of the kernels in the SVM. Okay. Okay, this is the end of the today's lecture. As I mentioned in the first, recent most machine learning technique have been formulated in based on the machine deep learning or the convolutional neural network or the recurrent neural network, but the SVM is still is the state of the art in some application, and the derivation of the SVM is really beautiful to relate compared to the other techniques. So if you can understand what is SVM and how can we derive the SVM well, then you can apply this concept to the another your machine learning technique. Okay, so this is the end of this section. In the next week, we will discuss the k-means clustering, mixture of Gaussian, and expectation and maximization.